Welcome to this deep dive, and today we're going to be looking into something um, pretty interesting. What does math have to do with philosophy?
Well, it's a question that people have been debating for centuries, but I think it gets even more interesting when you start thinking about quantum mechanics.
Exactly, and you've been provided with excerpts from the Stanford Encyclopedia of Philosophy's entry on quantum theory and mathematical rigor, and we're going to be kind of digging into this debate that's been going on for almost a century, a clash between two giants in quantum theory, Paul Dirac and John von Neumann. They had very different ideas about what role math should play in physics. And believe it or not, those disagreements are still kind of echoing today.
Yeah, it's not just a technical argument. It's really about how we even build our understanding of the universe, how we choose the tools to describe it, and what those choices tell us about the nature of reality itself.
So for our philosopher listening in, that you can kind of think of it this way: if you're trying to describe a dream, the language that you choose shapes, what details stand out and maybe even what conclusions you draw. And um, the same thing is true in quantum mechanics. The way we frame the math really influences how we interpret the physics. So we'll be exploring how these different mathematical approaches, these different approaches championed by Dirac and von Neumann, can lead to very different pictures of the quantum world. And then we'll see how their debate played out in the development of quantum field theory. And finally, we'll grapple with the philosophical implications of it all. Are you ready to go?
Yeah, absolutely. Let's untangle this fascinating knot of math and physics and philosophy.
Okay, so let's introduce our contenders. Dirac, as the source material explains, was known for his elegance and pragmatism. He wasn't afraid to bend the rules a bit to use mathematical tools that maybe weren't fully rigorously defined as long as they got the job done.
Yeah, he had a real knack for finding the simplest, most elegant mathematical expressions and using those to capture the essence of physical phenomena. So for him, the beauty of the math was a guide to the beauty of the physics underneath.
I think it's fascinating that he was okay with a bit of fuzziness in the math that seems kind of counterintuitive for a physicist.
Yeah.
What do you think was driving that?
Well, I think Dirac believed that excessive mathematical formality could sometimes obscure the real physics behind an argument. So he was really focused on results, on finding equations that accurately predicted experimental outcomes. And if a concept like the delta function, which wasn't rigorously defined at the time, helped him achieve those predictions, well, he embraced it.
It's kind of a whatever works attitude, as long as the results match up with reality.
Exactly. He trusted his intuition and his ability to extract meaningful physics from even somewhat unconventional mathematical tools.
Okay, but then we have von Neumann on the other side of the spectrum, a staunch advocate for mathematical rigor. He insisted on building quantum mechanics on as solid and logically sound a foundation as possible. In fact, he even expressed doubt about Hilbert spaces, which is remarkable because they're now considered a cornerstone of quantum mechanics.
Right, and for von Neumann, that foundation was the framework of Hilbert spaces. He saw them as the key to eliminating ambiguities and ensuring that quantum mechanics was built on, a really solid, logically consistent structure.
But wouldn't that level of straightness sometimes stifle creativity and exploration? Isn't there a danger of getting so caught up in the math that you kind of miss the bigger picture?
Yeah, that's a valid point, and it really highlights this tension between these two approaches. So while von Neumann's rigor, provides this very solid foundation, it can sometimes be seen as overly restrictive and potentially hindering the kind of intuitive leaps and creative insights that Dirac was known for.
So we've got this clash of personalities and philosophies, elegance versus rigor, pragmatism versus formalism. And this wasn't just an academic squabble. It had real consequences for how quantum mechanics developed.
Absolutely. This debate really goes to the heart of how we understand the relationship between math and physics. Is math just a tool we use to model reality? Even if the tools are a bit rough around the edges, as Dirac might argue? Or does the math itself reveal something deeper about the structure of reality, as von Neumann might suggest?
And these questions don't just disappear when we move from quantum mechanics to quantum field theory.
In fact, they become even more prominent. So quantum field theory, with its, complexities and infinities, really puts this tension between rigor and pragmatism on full display.
So it's like we've moved from a tennis match to a wrestling match with even higher stakes. Let's unpack that a bit. Our source material talks about this split in quantum field theory between these axiomatic approaches, which seem to be more in line with von Neumann's rigor, and the Lagrangian approach, which seems to have inherited some of direct pragmatism.
Yeah, that's a good way to put it. The axiomatic approach, as the name suggests, starts with a set of fundamental axioms, these mathematical statements that are taken as self-evident truths. And from those axioms, the entire theory is built up in a logically rigorous way.
So it's like building a house on a solid foundation, making sure each brick is laid perfectly.
Exactly. And this approach has its strengths. It provides this high level of certainty and consistency, ensuring that the theory is free from internal contradictions.
But it sounds like it might be a bit slow and painstaking,
Hmm.
right? What about the Lagrangian approach? How does that fit into this picture?
Well, the Lagrangian approach is more like building a house using a set of prefabricated modules. So it starts with something called a Lagrangian, which is a mathematical expression that encapsulates the dynamics of the system you're trying to describe.
So it's more about finding the right tools for the job, even if you don't fully understand how those tools were made.
That's one way to look at it, yeah. The Lagrangian approach is very powerful and has been incredibly successful in making accurate predictions about the world, but there are definitely some lingering questions about its mathematical rigor, particularly when it comes to things like path integrals.
Path integrals. Those sound a bit intimidating. Can you give us a quick explanation for our philosopher friend who might not be familiar with the ins and outs of quantum field theory?
Yeah, so imagine you're trying to figure out all the possible paths a particle can take between 2 points. A path integral is essentially a way of summing up the contributions from all those paths to calculate the probability of the particle ending up at its destination. It's a bit like considering all the possible routes you could take to get to work and then calculating the likelihood of arriving on time.
Okay, I think I'm starting to get the picture, but the source material mentions that path integrals raise some mathematical concerns. What are those concerns, and how do they relate back to this ongoing debate between rigor and pragmatism?
Well, one of the main concerns is that path integrals, as they're often used in physics, involve some mathematical manipulations that are not fully rigorous. They involve dealing with infinite quantities and making approximations that, while they seem to work in practice, lack a solid mathematical foundation.
So it's kind of like those fuzziness issues that Dirac was okay with, but now they're cropping up in a much more complex and challenging context.
Exactly. And this brings us right back to that core tension between Dirac and von Neumann. The Lagrangian approach, with its reliance on path integrals and other techniques, has been incredibly successful in making accurate predictions. But those successes have come at the cost of some mathematical rigor, leaving some mathematicians and physicists feeling a bit uneasy.
It's like building a beautiful bridge that seems to work perfectly but has some cracks in its foundation.
Mm.
You're glad it's standing, but you can't help but wonder if those cracks might cause problems down the line.
That's a great analogy, and it leads to a really interesting question. Is it enough for a scientific theory to make accurate predictions even if its mathematical foundations are shaky? Or do we need that rock-solid rigor to truly claim we understand something?
It's like asking if a beautiful building is still a success if the foundation has a few cracks, right?
That's a great way to put it. Some might argue that, the building is standing, it looks amazing, so who cares about a few cracks? Others would say those cracks could lead to serious problems down the line, that a truly successful building needs a foundation that can stand the test of time.
So in this case, the building is our understanding of quantum field theory, and those cracks are the mathematical uncertainties and the more pragmatic approaches.
Yeah.
And I guess it's up to us, the philosophers and the physicists, to decide how much those cracks matter.
Precisely. And this is where the philosophical rubber meets the scientific road. It's not enough to just do the math or conduct experiments. We need to think critically about the implications of our choices, about what kind of knowledge we're building and what standards we're holding ourselves to. But I think before we get too deep into the philosophical weeds, we should probably talk about one more key concept that really highlights this tension between rigor and pragmatism, and that's renormalization.
Renormalization. Okay, this sounds like something our philosopher friend might need a bit of help with. Can you break it down for us? Why is it such a crucial piece of this puzzle?
Sure. So renormalization is a set of techniques that physicists use to deal with infinities that pop up in quantum field theory calculations. It's like you're trying to calculate the energy of an electron and you get an answer that's infinitely large, which obviously doesn't make physical sense.
So infinities in the math, that sounds like a recipe for trouble.
It definitely raises some eyebrows. So renormalization provides a way to tame these infinities, to essentially subtract them out in a systematic way so that you end up with a finite, meaningful answer.
Okay, so it's a way of making the math work, of getting rid of those troublesome infinities. But where does the controversy come in? How does this tie back to the Dirac-von Neumann debate?
Well, the controversy lies in the fact that some of the methods used in renormalization, at least historically, have seemed a bit ad hoc, like mathematical tricks without a solid foundation.
So back to Dirac's whatever works approach, as long as the math spits out the right answers, we don't need to worry too much about how we got there.
That's how some critics see it. They
Hmm.
argue that renormalization techniques, feel like you're sweeping the infinities under the rug rather than truly understanding where they come from and what they mean.
So we're left with this fascinating tension. On one hand, renormalization is a powerful tool that has led to incredibly accurate predictions, some of the most precise in all of science. But on the other hand, there are these lingering doubts about its mathematical rigor, about whether it's truly giving us a deep understanding of the quantum world or just allowing us to cleverly manipulate the math to get the answers we want.
And that, I think, is the perfect encapsulation of the Dirac von Neumann debate in a nutshell. It's a debate that continues to this day, a constant reminder that in our quest to understand the universe, we're always walking this tightrope between the elegance of pragmatism and the certainty of rigor.
And that's a great place to pause. For now, we've set the stage, introduced our key players, and highlighted this fundamental tension between how they approach the math of quantum mechanics. And next time, we'll see how this debate played out in the development of quantum field theory and explore some attempts to bridge the gap between these seemingly opposing viewpoints.
I'm eager to dive into those fascinating developments. It's a journey that takes us to the very edge of what we know about the universe and forces us to confront some of the deepest philosophical questions about the nature of reality itself. Picking up where we left off, let's look at a specific example that really kind of brings this tension between rigor and pragmatism into focus.
Okay, lay it on me. What's this example that's going to blow our philosopher's mind?
Let's talk about unitarily inequivalent representations in quantum field theory.
Whoa, hold on a second. I know we're talking to a philosopher here, but even I'm feeling a bit lost. Unitarily inequivalent representations. That sounds like something you'd find on a blackboard in a theoretical physics lab, not in a philosophy seminar.
Fair enough. Let me try to paint a picture.
Mm.
Imagine you're looking at a sculpture from different angles. Each view kind of gives you a different perspective, right? But it's still the same sculpture.
Okay, I'm with you so far.
Now imagine that those different views are like different mathematical representations of the same physical system in quantum field theory. Each representation uses a different Hilbert space, which is basically a mathematical framework for describing quantum states.
So different mathematical languages to describe the same quantum reality.
Exactly, but here's where it gets interesting. These representations are called unitarily inequivalent because there's no simple mathematical transformation that can convert one into the other. It's like those different views of the sculpture are so distinct that you can't easily morph one into another.
Okay, now I see where the philosophical puzzle comes in. If these representations are truly inequivalent, does that mean they're describing different realities? Like maybe there are multiple quantum worlds, each corresponding to a different mathematical representation?
That's precisely the question that philosophers and physicists are grappling with. Some argue that unitarily inequivalent representations might point to different physical realities, that the math is telling us there's more to the universe than meets the eye.
That's wild. Just from a choice of how we represent the math, we're suddenly talking about multiple realities.
It is mind-bending, isn't it? But there's another side to this debate. Some maintain that these different representations are just different ways of describing the same reality. It's like using different coordinate systems to map the same terrain. The map might look different, but the underlying landscape is the same.
So one reality is of multiple mathematical perspectives. I'm starting to see how this gets philosophical fast.
And it doesn't stop there. The debate gets even more intricate when we consider something called effective field theory.
All right, hit me with it. What's effective field theory, and how does it add fuel to this philosophical fire?
Okay, think about it this way. You have a map, and it seems to be a pretty accurate representation of the world, but then you discover that your map is just a small part of a much larger world, a world with landscapes and features you hadn't even imagined.
So effective field theory is like realizing that our current map of quantum field theory might just be a tiny piece of a much grander picture.
Exactly. Effective field theory suggests that maybe quantum field theory as we currently understand it isn't a fundamental theory after all. It might just be a low-energy approximation of some deeper, more fundamental theory that we haven't yet discovered.
Whoa, that's a pretty big implication if quantum field theory is just an approximation. What does that say about the reality it describes? Are the particles and fields we talk about just emergent phenomena, like the ripples on the surface of a pond?
Those are really profound questions, and they lead us to a whole new level of philosophical inquiry. If quantum field theory isn't fundamental, then what is the true nature of reality that lies beneath this emergent level of particles and fields?
I'm starting to feel a bit dizzy from all these layers of reality, but I guess that's what happens when you start probing the very foundations of physics.
Yeah, it's a testament to the power of these debates that they can lead us to such profound philosophical questions, you know? They force us to confront the limits of our knowledge and to consider possibilities that might seem strained or even paradoxical.
Yeah, it's a good reminder that sometimes the most profound insights come from questioning our most basic assumptions, even those that seem so obvious we hardly even notice them.
Speaking of questioning assumptions, remember how we discussed constructive quantum field theory? This area of study represents a really fascinating attempt to reconcile these contrasting approaches of Dirac and von Neumann.
Right, we talked about it briefly, but I think our philosopher friend could use a deeper dive into what constructive quantum field theory is all about. Can you unpack it for us?
Yeah, sure. So, constructive quantum field theory, or CQFT, is essentially an attempt to build specific models of quantum field theory in a mathematically rigorous way. The goal is to start with those rock-solid axioms like von Neumann championed, and then step by step build up a model that not only satisfies those axioms, but also corresponds to those successful Lagrangians that physicists use in those more pragmatic approaches.
So it's like saying, okay, we have these beautiful abstract axioms over here, and we have these messy but effective Lagrangians over there. Can we create a model that bridges those two worlds, a model that's both rigorous and useful?
That's a great way to put it. It's like trying to build a Lego model based on a fuzzy blueprint. CQFT is like meticulously figuring out each brick and connection to create a solid, accurate structure that reflects the blueprint, but is also structurally sound.
I love that analogy. But how successful has this bridge building been? Has CQFT managed to bring together the elegance of Dirac and the rigor of von Neumann?
Well, it's been a challenging journey, but there have been some remarkable successes, especially in constructing models in lower dimensions, like 2 or 3 dimensions, which are simpler than our four-dimensional spacetime.
So baby steps towards a grand unification.
Yeah, you could say that, but the Holy Grail, constructing a rigorous four-dimensional model that corresponds to the Lagrangians we use to describe the real world, that's still a work in progress.
It sounds like a monumental task, trying to capture all the complexity and subtlety of the quantum world in a model that's both mathematically sound and physically accurate.
It is, but the progress that's been made is encouraging. It shows that it might be possible to have both, to have a quantum field theory that's beautiful in its rigor and powerful in its ability to describe the world around us.
Okay, so we've got these two camps, the axiomatic folks and the Lagrangian folks, each with their own strengths and weaknesses. But then we have CQFT trying to bridge the gap to create this unified theory that's both rigorous and effective. But how does all of this play out in the real world of physics research? Do physicists actually pick a side and stick to it?
It's a great question. In the day-to-day practice of physics, it's less about choosing a side and more about using the right tool for the job. Sometimes a more pragmatic approach, even if it's not fully rigorous, can lead to breakthroughs that a stricter axiomatic approach might miss.
So there are times when Dirac's boldness is called for, when you need that intuition to push the boundaries, even if you don't have all the mathematical justifications neatly lined up.
Absolutely. There are moments in research when you need to be willing to play with the math, to follow your intuition, even if it leads you down some unconventional paths. But then once you've made some progress, you might need von Neumann's rigor to come in and kind of clean things up, solidify the foundation, and make sure you're not building on shaky ground.
It sounds like there's this delicate dance between the two, a constant interplay between intuition and rigor.
And finding that balance, knowing when to be bold and when to be cautious, when to trust your intuition and when to demand proof. That's one of the things that makes science so fascinating. It's not just about blindly following rules or formulas. It's about creatively engaging with those rules, pushing them to their limits, and sometimes even breaking them in the pursuit of deeper understanding.
I'm sensing a theme here, this kind of recurring motif in our exploration of quantum theory, this dance between these seemingly opposing forces, rigor and pragmatism, intuition and logic, the abstract and the concrete. It's like these tensions are what drive the field forward, what push us to constantly question our assumptions and refine our understanding.
And that's where the philosophical rubber really meets the road. It's not enough to just do the math or conduct experiments. We need to grapple with these deeper questions about the nature of knowledge, the role of mathematics in describing reality, and the very meaning of what it means to understand something.
And on that note, I think it's time for us to take a step back and reflect on everything we've covered so far.
Yeah.
We've journeyed from the historical clash between Dirac and von Neumann to the complexities of quantum field theory, exploring the tension between rigor and pragmatism, the puzzle of unitarily inequivalent representations, and the quest for a unified theory through constructive quantum field theory.
Yeah, it's been a whirlwind tour, but hopefully our philosopher friend is starting to see how these seemingly abstract debates about mathematics have profound implications for our understanding of the universe and our place within it.
But before we wrap up, there's one more piece of this philosophical puzzle that I think deserves our attention, and that's the question of interpretation.
Ah, yes, the thorny issue of interpretation. I was wondering when we'd get to that. It's one thing to develop the mathematical framework of quantum theory, but it's another thing entirely to figure out what it all means. What is this mathematical edifice telling us about the nature of reality?
And this is where the philosophers really come into their own right. They're the ones who help us grapple with those big existential questions that the math alone can't answer.
Precisely, physicists might develop the equations, but it's often the philosophers who help us interpret those equations, who help us make sense of this strange and counterintuitive world that quantum theory reveals.
So for our philosopher friend who's been patiently listening to all this talk about math and physics, get ready, because next we're going to dive into the deep end of philosophical interpretation, exploring some of the most mind-boggling ideas about the nature of reality that quantum theory has inspired.
I can't wait. It's a journey that takes us to the very edge of what we know and forces us to confront the limits of our understanding.
All right, so we've explored the math, we've kind of glimpsed the complexities of quantum field theory, and we've even dipped our toes into, the philosophical waters of multiple realities and emergent phenomena. But now let's really dive into the deep end of interpretation.
Yeah.
Where do we even begin?
Well, one of the most striking things about quantum theory, I think, is that it really challenges some of our most basic assumptions about how the world works.
Okay, give me an example. What kind of assumptions are we talking about?
Well, take the idea of determinism, for instance. Classical physics. The physics of Newton and Galileo paints this picture of a universe that's predictable, like a clockwork mechanism. If, the initial conditions of a system, you can, in principle, predict its future with perfect accuracy.
So a cause and effect universe, everything neatly laid out.
Exactly. But quantum theory throws a wrench into that neat picture. It introduces this inherent element of randomness, of uncertainty. We can't know both the position and momentum of a particle with perfect accuracy. There's always this fundamental limit to what we can know.
So it's not just that our measurements are imperfect, it's that the reality itself is fundamentally fuzzy.
That's one way to interpret it. And this indeterminacy has really profound philosophical implications. If the universe isn't deterministic, does that mean there's no such thing as free will? Are our choices predetermined, or is there genuine randomness at play?
Whoa, those are some heavy questions. I'm starting to see why philosophers get so excited about quantum mechanics. It's not just about the science. It's about what the science tells us about the human condition,
Yeah.
about our place in the universe.
Exactly. And there's no shortage of interpretations vying to make sense of all this. Some interpretations, like the Copenhagen interpretation, embrace this indeterminacy, arguing that the act of measurement, fundamentally alters the system being measured.
So it's not just that we can't know everything with certainty. It's that the very act of knowing changes the reality we're trying to know.
Precisely, other interpretations, like the many worlds interpretation, take an even more radical approach, suggesting that every quantum measurement causes the universe to split into multiple branches, each representing a different possible outcome.
Okay, multiple universes splitting off every time we make a measurement. Now, that's a mind-blowing idea.
It definitely challenges our intuitive understanding of reality. But the point is, there are many different ways to interpret the mathematical formalism of quantum theory, each with its own strengths and weaknesses, its own set of philosophical baggage.
So it's not like there's one right answer, one definitive interpretation that everyone agrees on.
Not at all. The debate about interpretation is still very much alive, and it's a debate that involves not just physicists and philosophers, but also mathematicians, computer scientists, and really anyone else who's interested in the fundamental nature of reality.
It's just fascinating how this one scientific theory, quantum mechanics, can open up so many philosophical avenues, so many different ways of looking at the world. It's like a prism that refracts our understanding of reality into this spectrum of possibilities.
And that, I think, is one of the most beautiful and humbling aspects of science. It doesn't give us all the answers, but it gives us the tools to ask better questions, to explore deeper mysteries, and to constantly refine our understanding of the universe and our place within it.
So for our philosopher friend who's been on this whirlwind tour of quantum theory with us, what's the big takeaway? The one idea they should carry with them as they kind of ponder the mysteries of existence?
If I had to choose one, it would be this quantum theory challenges us to expand our minds, to embrace uncertainty, and to accept that reality might be far stranger and more wondrous than we ever imagined.
I think that's a perfect note to end on. It's been an incredible journey, and I hope our listeners have enjoyed this deep dive into the fascinating world of quantum theory and its philosophical implications.
Until next time, keep questioning, keep exploring, and never stop marveling at the universe and its mysteries.